Hello, let's learn about matrices. So if you watched vectors, matrices are just 2D vectors. So instead of being one array of numbers, matrices is like an array of arrays. So 2 dimensions. You see, this is how we denote generally matrix, starting from some number that has index 1, 1, or in programming, this usually has index 0, 0. And all the way to 1n. N denotes the number. 1 means like the first row. So 1 is always same in the first row. Second row here, 2 is always same. At the end, we have m is the number of rows and n is the number of columns. So the second number is the column index. So if number of rows and number of columns is equal, then that's a square matrix. Matrices usually represent neural network weights. They can also represent gradients in the backpropagation. So we learned about gradients here, so they can be saved in matrices. Other than neural network applications, matrix also represents linear transformations. So if you have a vector, you multiply that vector with a matrix, you will actually rotate that vector. By multiplying it with a matrix, you rotate it or stretch or squish. This is one of the main principles behind the new muon optimizer that's the best new optimizer for neural networks. So what it does is muon optimizer instead of, so it's gonna transform matrices within neural networks that would otherwise stretch or squish and rotate weights and vectors. Muon transforms those matrices such that they only rotate. They don't stretch or squish vectors. So that's like the new trick. And I'm also researching that. So it turns out if you have matrices, if you transform matrices so they just rotate vectors within neural networks and they don't stretch or squish, then neural networks learns faster with less data. But more on that later. This topic was actually very confusing for me when I first heard about it. So don't worry if it's a bit confusing, you don't understand. You'll eventually learn it. Here are some example matrices. So 1, 2, 3, 4. So here, if I say first row, this is the first row, okay? First column is this. If we want to add these matrices, we simply add each element at the same position. So 1 plus 5, 2 plus 6. So here, 1 plus 5 is 6, 2 plus 6, 8, and then these elements here, etc. Then we can also multiply 2 times A. So if we multiply 2 times matrix A, we just multiply every element with the scalar. Matrix multiplication, this is extremely important. This is used in neural networks. This is how, when they're learning, or generating new things, you multiply input vector or maybe activation vector, activation matrix with the weight matrix. So you do dot product. So if you have two matrices like this, the way you multiply them is you do dot product between first row and first column here. So what that means is 1 times 5 plus 2 times 7. So 1 plus 5 would be 5. No, 6. Wait, sorry. 1 times 5 is 5. And 2 times 7 is 14. So 5 plus 14, 19. And we write that number 19 at the intersection of these two. So you see the first element here is contained in both of them. So we write that 19 at the result at the place of this first element. So if you don't understand, let's check this again. So you see, so we go first row and first column of the other matrix, and then we go, so 19 is written here, okay? So for this 22, we're gonna do this first row and this second column, because you know they intersect at this second element. So that's gonna be 22 here, etc. So and then we do this row and this, sorry, this column. No, sorry. So we are looking at the rows. So we say this row and this column. And so we put it here in this corner. And then bottom row and the second column here. And that's it. That's the matrix multiplication. So this needs a bit of practice. Then we have key matrix transformations and properties. So we have transpose. So this will swap rows and columns. So you see A is 1, 2, 3, 4. A transposed is 1, 2. Now this is the row. So this row became a column. And 3, 4. So this row became a column here. And determinants only exist in square matrices. So non-square don't have determinants. So the formula for determinant is A times D. So this diagonal, A times D, minus this diagonal, B times C. And determinants are very useful. They're also useful in what I was explaining in muon optimizer in some ways. So we'll learn more about determinants later, but just know how to calculate it. This diagonal minus this diagonal. And then we have inverse. So don't confuse inverse and transpose. So inverse is, so if we have A, then A inverse. If we multiply A and A inverse, it gives us identity matrix, which is just shown here. So it can be like, it has ones on the main diagonal and zeros everywhere else. So that's identity matrix. And so when you need to find like this matrix A inverse such that when you multiply the A, whatever matrix that is, if you get the identity matrix, then that's the inverse of A. And so this is formula to calculating inverse for just 2x2 matrix. I think for higher matrices, formula becomes a lot more complex. But that's all I want you to know. So what identity matrix is and what inverse is. So here we have special types of matrices. Identity matrix, ones on diagonal, zeros elsewhere, is what I just explained. Zero matrix is all zeros. A diagonal matrix is non-zero numbers at the diagonal. So any numbers at the diagonal, not just ones. And others are zero. Symmetric matrix is where inverse is equal to the matrix. Orthogonal matrix. So that's a matrix where if you look at each row separately as a vector, those vectors will be 90 degrees. So if you draw a vector for the first row, and vector for the second row, and vector for the third row, they don't need to be in 2D space. But they can be like in any amount of dimensions. But they are 90 degrees between each other. So that's what we want to turn our weight update matrix in neural network with. So I was mentioning muon optimizer, and that muon optimizer makes neural networks learn faster. This is how it makes it learn faster. It transforms matrices into orthogonal, or I should also say orthonormal. But orthogonalization is one part. Because orthogonal matrix, when you multiply that with a vector, or vector with that matrix, it will just rotate the vector. It will not stretch the vector or squish the vector. So that's why we use orthogonal matrices. But we will learn a lot more about this later. So I guess if you already know this, you would understand, but if you don't know this, it's tough to understand from like this explanation. This requires deeper reading, understanding, learning practice. So remember that matrix multiplication order matters. If you have matrix A multiply matrix B, the result is not going to be the same if you swap them. If you say B multiply A. And one more important rule. So for the first matrix, for the left matrix, number of columns, so one column, two columns, must be equal to the number of rows in this right matrix. So one row, two rows. Okay, now it's equal. So now we can matrix multiply them. If it wasn't equal, we wouldn't be able to matrix multiply them. That's it for this video. See you in the next one.